All right, welcome back. We're going to talk, our next topic of discussion is the kinetic molecular theory. This is talking about the fact that all of particles, every particle all around you is constantly in motion. Some things are vibrating in place, the particles are, which would end up being in the terms of a solid. Other things are free to move past one another, like in terms of a fluid, gases and liquids, for example. And we're going to look at the kinetic molecular theory, what that means, and then look at models, that the particulate diagrams, and then some graphs as well. So gases made up of these particles, pretty large amounts of energy, relatively speaking. Again, no definite shape or volume. They're going to take up as much space as possible. They don't have any intermolecular forces holding them together for the most part. And so they're able to kind of spread out as far and wide as they can go. One of the things that kind of is interesting, though, is that because they're spread so far away from one another, and there ends up being a lot of empty space in between them, so we can compress them. And you've seen that before when we look at different gases that are compressed, like if you've ever seen a helium tank or a propane tank, like you might have an LP tank or something like that that you might have for your gas grill, for example. The actual material inside there is a liquid because they've compressed it so much. They've taken and pushed those molecules together so closely that now the intermolecular forces are able to take over, and it's turned them into a liquid. But if you remove that pressure and give them more room to move about, they're going to move away from one another, overcome that intermolecular force, and go back into gas. And so that's why those tanks are built the way they are, is to keep those things under such high pressure that they'll stay as a liquid. But given the opportunity to spread wide, they will do so because they'll overcome those intermolecular forces and turn back into a gas. So when we look at pressures, pressure is going to be exerted on the side of the container when these gases are in them. And we can measure that pressure typically in atmospheres, millimeters of mercury, or torr. There are other ones out there, but they don't typically use them on the AP exam. Kilopascal and Pascal is also used sometimes as well. So keep your eye out for that. You do have some conversions of these, and you should become familiar with those on your formula sheet so that you know where to grab them and be able to use them in your test. So use that formula sheet, see if you can convert from millimeters of mercury to ATM, and then also see if you can convert between torr and ATM. Your dimensional analysis will come in handy here if you would like to take advantage and use that. So here are the answers you should have ended up with for those. So you can pause the video and check your answers if you'd like. All right, getting back into kind of the nitty gritty of the kinetic molecular theory, there are 5 things that we have to understand. Gases are composed of tiny particles. Size is negligible, and the average distance between them. So that means the volume that they actually take up as particles tends to be very negligible compared to the volume of the container. And so because of that, the total volume that a gas fills is almost all of the empty space. So things that we can see in terms of the gases is that they're compressible. So we talked about that in terms of like our propane tanks and our helium tanks. And it tends to be consistent with the assumption that the actual gas particles have very little volume compared to how much they would take up in their container. So second thing that we talk about is gas particles move randomly. They move in straight lines and move at various speeds. The forces then of attraction or repulsion between the two gas molecules tend to be pretty negligible, except when they collide. So when they do collide into one another, the collisions are elastic, so there's no kinetic energy lost. The collisions are what creates the pressure on the sides of the container. So if you increase the temperature, you're going to increase those collisions, and that's going to lead to an increase in pressure. So elastic collisions are consistent again with the observation that when left alone in the container, they don't appear to lose their energy. They tend to stay the same amount of energy, and they don't just randomly convert back into a liquid. So if they were losing energy, those IMFs would start to take hold, and then we would start to see liquid forming, and we don't see that. So that's why we believe that they are elastic. And then the last postulate is that the average kinetic energy of a gas is proportional to the Kelvin temperature. That's why we have to have things in Kelvin. And as a result, all the calculations involving gases, they need to be carried out and converted into Kelvin. So Kelvin eliminates the problem with negative temperatures. If we did negative temperatures, then we might end up with negative volumes, and that doesn't work. We can't have a negative volume. So we do have some limitations here. For example, like I was saying before, we can liquefy gases. We've talked about that with the helium tanks and propane tanks. And that means that we actually have real gas particles that do attract one another. That's why I said they mostly overcome the IMFs. But we tend to be able to get a situation where they're able to kind of stick together and form into a liquid. And when that happens, then they're acting more like real gases instead of ideal ones. So that's why we use real in quotes here. So when do we deviate or move away from the ideal gas law? Well, I always think of it in terms of what's going on, what would lead to an increase in intermolecular forces. And what would do that would be high pressures, because at high pressures, you're pushing those gas molecules closer to one another. If they're getting closer to one another, just like if you get magnets close enough to one another, they're going to attract one another, and that's going to lead to your intermolecular forces. And then low temperatures will also do it, because if the molecules start moving around much more slowly, they'll have a tendency to come upon one another closer. And so because of that, those intermolecular forces have a ability to kind of take hold and form into the liquid phase. Again, under these conditions, high pressure, low temperature gases are said to behave less ideally. And that is a lot. I've seen many AP questions on that, where they'll ask you, what situations would cause this gas not to act ideal. And you need to think about that. And if you think about, like, okay, it's temperature and pressure, you should be able to remember that. And then you're like, but which one's which? And if you think about, okay, if I push things together closer with high pressure, and if I slow them down enough, that's going to cause them to go into the liquid state. Okay, so the actual pressure of a gas is lower than one would expect when assuming there's no attractive forces between the particles, because in a real gas, the particles are going to be attracted to one another. They collide against the walls with less force, and they're also going to do that if the temperature is low. And so because of that, you need to correct the pressure by adding a factor in. That factor is called van der Waals equation. This is the formula. You don't need to perform this calculation for this equation on the test, but it's kind of nice to be able to see what's going on and how that relates. So for example, gas particles have relatively strong interparticle or intermolecular attraction for one another. And if their pressure needs to be corrected by a large enough factor, that relatively large gas particle would have correspondingly relatively large values of B here, since they take up a larger volume. All right, so that takes us to the end of our gas unit.